I know that the only thing between now and the reception is my talk. So I'll try to make it on time. But this is going in the other directions. This is work that we've developed at Yale as part of this collaboration for the Center for Quantum Dynamics on Modular Quantum Devices. I'm the lead PI, and it's integrated at the moment. This is phase 1 by Michel Deboré at Yale, who is an expert in building quantum processors. Ethan Geba from University of Michigan, Lea Santos from UConn, and Sabri Kais from Purdue. So these are the PIs of this center, but the real heroes are the people who actually did this work. Ningil and Ellen in my group, and Ellen graduated from Ethan Geba's group, and Yuchen and Andrew from Sabri Kai's group. They also put together this very nice tutorial on the dynamics of open quantum systems, non-Markovian quantum and dynamics with a generalized quantum master equation that if you go to my webpage, you will find it under the center. This is the webpage of the center.
You don't see it.
Oh, you don't see it. So, and here, if you click on Outreach, you will see this tutorial, which has everything I'm going to be talking about now. So, for instance, this Jupyter notebook, it walks you through the code and the description of how to actually reproduce all the results that we publish in our papers, and how to use tensor networks for computing the memory kernels of the Nakashima-Zwanzig equation, and with that, how to propagate the dynamics for the reduced density matrix. So how can I go back now? The code is here. So actually, you have to go through the whole thing. But it's a very nice tutorial, and I really want to emphasize that they're the ones who deserve all the credit for all that work. If I can come back to this other page. I don't know how to do it. There you go. So the whole idea of this project and this Center for Quantum Dynamics started a few years ago when we published this work on demonstrating that we could use this quantum processor, which is very simple. It's two cavities in a solid piece of aluminum. That is, the two cavities are empty, and over there you can put photons. And the light that is injected in these cavities will be coupled with this transmon that is inserted in that little hole that basically makes connection between the two cavities and a resonator that can interact with it. And what we demonstrated is that with a single piece of hardware like this one, which is the size of comparable to a quarter, we could actually calculate the vibronic spectrum of triatomic molecules by using each of the cavities as the basis for the normal modes. In this case was the symmetric stretch and the bending of water, and we were able to compute the Frank-Condon factors, which is a calculation which is impossible with conventional quantum computers like the IBM, because it would require circuits with a depth of more than 1,000 gates. Nowadays, the limitation in terms of number of gates, the circuit depth is of the order of 100 or so. So with this in hand, we were really interested in our problem, which is whether we could use that type of hardware for simulating non-Markovian dynamics for open quantum systems. And these were the systems that we had in mind. And that's why this morning I suggested realistic models to keep in mind somewhere in the list of potential benchmarks or comparisons for existing methods and new methods. We were, as chemists, we are very much interested in charge and energy transfer, as well as photochemistry and photosynthesis. And my collaborators, the physicists, are interested in modeling quantum circuits and quantum optics. All of these involve non-Markovian quantum dynamics. And our input into this direction was not only that work on the simulation of the vibronic spectrum of triatomic molecules, but on our previous work on using matrix product states for simulating quantum dynamics in molecular systems. So we had developed these methods for multidimensional non-adiabatic quantum dynamics, global optimization, and we thought these techniques of propagating a wave function could be extended to simulating density matrices and therefore open quantum systems. And the work I'm going to be talking about today is mostly these two papers, and I will just mention at the end the work that concerns the third paper. And I give you a very simple description of what the talk is about. Essentially, the first paper is this use of tensor train thermal field dynamics to compute the memory kernels that are necessary for the integration of the generalized quantum master equation. And the model system that we use is this model of charge transfer that is, it's been Boson model coupled to 60 harmonic degrees of freedom of the bath with this Hamiltonian. And simply, if we had an efficient way of representing the density matrix, then we could propagate it and evaluate observables such as the population, the donor, the acceptor, and so on. And that's exactly what we do with the tensor train, full tensor train implementation for this problem. Simply, this superoperator, this propagator, is matricized, and the density matrix is matricized, is vectorized. So now we have matrix vector multiplication. The vector is a tensor train. The propagator is a tensor train matrix. And we evolve that initial density matrix according to this propagator. And we demonstrate that we can actually simulate the dynamics properly. And then we compare to the favorite method in the room, QAPI. And so we have here QAPI on top of our calculations. And we also compare to the dynamics obtained with the generalized quantum master equation. And we do a couple of different ways of implementing that simulation with the GQME. One is using projection into all of the matrix elements of, I would call these electronic degrees of freedom. So you can think of electron on one well corresponds to one electronic state, and the other well corresponds to another electronic state. The bath are the nuclear degrees of freedom. So from now on, I will be talking about electronic and nuclear degrees of freedom. But one could simulate the dynamics for the reduced density matrix associated, all of the reduced elements of the reduced density matrix of the electronic degrees of freedom, and then compute, for instance, populations as a function of time. And you see that those that corresponds to populations only versus single population of full. That means that we simulate the dynamics for the generalized master equation that projects all the dynamics into either one of the elements of the reduced density matrix of the electronic degrees of freedom to only the diagonal matrix elements. We propagate only the diagonal matrix elements, or all of the matrix elements of that reduced density matrix, With all of those, we get the same dynamics as we obtain with a full tensor trained propagation of the system, and also the same dynamics as you get with QAPI. So
what do you mean by this? You're only plotting sigma z, which is diagonal.
yes.
So why does it matter if you are computing off diagonal or not?
Yes, and we could propagate the dynamics for only the off diagonals if you wanted. And in the paper, we include those too. So basically what I'm going to explain in this presentation is that one can simulate the dynamics for a subset of matrix elements of the reduced density matrix and derive a master equation for that subset. And in fact, one can select only one element. and when you compare that with propagating all of them, you get the same answer. So that means that it's a different master equation, but it gives you the same answer.
Yeah, I understand there's some decoupling there. Sorry, I understand there's some decoupling there, but the kernel will need the off-diagonal elements too.
When you compute the kernel, you have to sum over all of this. Yeah. But what I'm saying is that the kernel that is obtained corresponds to the subset. Anyways, I'll show you all that. But this is basically the comparison that these are the results that we obtain with those various different flavors of the generalized quantum master equation. And then we implemented these same simulations on a quantum computer, and the IBM quantum computer, by finding a way of propagating the reduced density matrix with a unitary propagator, even for this case of dissipative dynamics, using the dilation theorem that enables to transform a contraction into a unitary propagator. And with that quantum circuit, and with one of the IBM quantum computers, we demonstrated that we can simulate the dynamics of this generalized quantum master equation and good agreement with the tensor train simulation. So the usefulness of the development of these methods, and goes both ways, is good for simulating quantum circuits, and also for validating the results that one obtains with the actual calculations on the quantum computer. So with that already said, you know what we've done and what are the results. But some of you might not, some of you already know all this, and so I don't need any further clarifications. But for those of you who might want to know more about how we actually did it, so I'll walk you through the various different representations. Well, the first one is...
sorry, but that plot, why does this look so strange? The sigma z of t.
In what sense?
So it is the top, the highest value is decaying, but the lowest value, is this really sigma z of t? So I mean, it could be shifted, but it does not seem to, it won't equilibrate about, the oscillations are not about the average of this curve.
This one is compared to the early time dynamics of this, right? Well, no, is this a different model? This model too?
Yeah.
And
so the minimum of those oscillations is at the same place, whereas the maximum.
Yeah, so I can check the model for this and we can compare, yeah. But overall, the benchmarks to the actual simulation of tensor train look very good. And so basically the whole idea of this tensor network representation, as it was extensively discussed in this meeting, is not to work with a full rank object, but to work with a tensor cores and to build this representation, as Oliver explained yesterday, with a skeleton decomposition, exploiting the magic of factorization, where all of the elements of a matrix can be obtained from a much smaller subset if this object is low rank. And the specific way we build these tensor networks these tensor trains is with what Oliver described yesterday with this method by Ivanov Seledet and Trishnikov, where one selects the subset of rows and columns that gives a representation, good approximation for the tensor of interest. And this is in a multidimensional, multilinear algebra representation of the tensor, where this intersection matrix needs to be inverted or pseudo-inverted and maximize the volume of that. With that approach, we have demonstrated, as I mentioned, that one can simulate the dynamics, for instance, all of these hydrogens that are involved in hydrogen bonding in this DNA, piece of DNA, follows dynamics that very efficiently because it's a sufficiently low rank object, as well as we have used that representation for global optimization, works very well. And also photodissociation dynamics, which is another one of those applications that I mentioned at the very beginning that we are very much so. The multidimensional wave packet of the 69-dimensional nuclear wave function is very efficiently represented, and one can study, for instance, the X-ray spectroscopy of these with a full representation. So these are the kind of realistic applications that we are very much interested in, and where we are going to be testing these methods. Now, in terms of the simulation of the dynamics of the reduced density matrix, this is basically the full GQME, where in order to obtain the propagation of this reduced density matrix, one needs the memory kernel. And that memory kernel, in addition to memory kernel, the projected Liouvillean, and the memory kernel has this expression in terms of sufficiently well-chosen projection superoperator that projects the density matrix into a subspace that is a subspace of interest. And as I mentioned, it could be all of the electronic, all of the elements of the electronic reduced density matrix or a subset of those. And the equation of motion for that reduced density matrix is the same as the equation of motion for the propagator. They both follow the same GQME. Okay, so now the question is, how we obtain, well, first of all, where this equation comes from. Many of you have already know that, but what we do is simply starting from the Liouville equation. So starting from the Liouville equation, we apply this projection operator into the subset, and we get the equation of motion for the projected density matrix. And what we obtain that is in terms of the projected density matrix in the orthogonal space. So we do the same thing for that one. We obtain an equation for the evolution of the elements of the reduced density matrix that are projected in the orthogonal space. We integrate it formally, and then substituting this into the previous equation, we get the GQME that is the Nakashima-Zwanzig equation. So that gives us the expression of what the memory kernel is. And we see that this is the projected Liouvillean. This term will go to 0, and that is the memory term once we trace over the bath. So to prove that is simply, getting the time derivative of, this is the same expression for the proving that the left-hand side corresponds to the evolution of the reduced density matrix elements is simply because that trace is equal to 1. The first element corresponds to the projected Liouvillean. The third term goes to 0. The second term goes to 0, and the third term gives this expression in terms of the integral of the kernel. Then we get the derivation of what the kernel is. And I'm explaining this because we're going to use the same approach to obtain the subset, simply with a different choice of the projection operator. Instead of using this projection operator that puts all the dynamics into the electronic degrees of freedom and factors out a time-independent nuclear density matrix, we are going to be here summing over a subset of those electronic degrees of freedom. So once we get the expression of the kernel, we can go ahead and find an equation of motion for that. Simply straightforward derivation. And we find that if we can integrate it like this, and this is the standard way of propagating the memory kernel, in terms of this function u, whose derivative corresponds to this non-projected input function. Very good. So with this in hand, as it was mentioned yesterday, once you have this equation of motion, one obtains the kernel in the first step, and then with the first kernel, you obtain the second one, and so on and so forth. So it's a mapping that allows you to obtain all of the memory kernels. Here's the other option that we call the modified GQME, and you can make your choice for the projection operator, but here's the projection into a subset of electronic elements. So basically, simply one computes the trace of this is the coefficient in the expansion in this basis. So it's the trace of the density matrix in that corresponding to that element, pointing in that direction, and you sum over all of the elements that you want to include in your set. And with that, you obtain a projected density matrix in that subset or subspace of elements of the reduced density matrix associated with electronic degrees of freedom. So this is what this object is about. And with that, we obtain the corresponding GQME, where we have the sums that are required to evolve each of the elements in that subset of elements of the reduced density matrix. And the corresponding memory kernels that are involved in these GQME, again, need to be computed as matrix elements with this argument. You should notice also that this modified GQME has this inhomogeneous term, so we also need to include that in the evolution of the reduced density matrix elements. So now, how do we actually compute those elements that are required, those U elements that are required to evolve these memory kernels? So what we use is this tensor train thermal field dynamics that basically represents the density matrix in terms of the thermal wave function. So basically here now, this wave function has physical degrees of freedom and copies of those physical degrees of freedom that we call the fictitious degrees of freedom. And we are going to be tracing over the fictitious degrees of freedom. And one can show that this thermal wave function gives a representation of the density matrix that evolves according to the Liouville equation, and also gives you all the ensemble averages that coincide with those obtained directly with the Liouville equation of motion, but evolves according to the Schrodinger equation. So that connects with our earlier work on all the work that we've done with propagation of wave functions. So basically, the only thing that is required is to expand the Hamiltonian with the space of those fictitious variables. But the physical Hamiltonian is the only one that rules the dynamics of that thermal wave function. And the initial state, the thermal state, it can be obtained directly by squeezing vacuum, where this gives a very efficient way of generating an initial density matrix for this particular case when the bath is a bath of harmonic oscillators. So let me show you that, in fact, this is the case, that this function evolves according to the Schrodinger equation, that what you obtain with the ensemble averages are the correct ensemble averages. There's no approximation. It's just an exact way of doing quantum dynamics. So, so first of all, this is what I don't know what that is about, but this is what the thermal wave function is with those fictitious degrees of freedom, and this is when it is at thermal equilibrium initially, and one can really integrate this and find that this is the operator that squeezes vacuum and generates the thermal state that corresponds to the state where we have the Boltzmann population for each of the states. And thermal ensemble averages are obtained just as if it was a expectation value of any operator, but what it gives is the thermal ensemble average of a mixed state. So this is the nice thing about this representation. Also, the thermal density is exactly what you get by computing the density matrix with this thermal wave function and tracing out over the fictitious degrees of freedom. The evolution of the Schrodinger equation for that thermal wave function leads you to an evolution of the density matrix that you construct by tracing out the fictitious degrees of freedom that is exactly the Liouville equation. So there is no approximation. And it has one more perk to this formulation, that you can subtract I cross any function, any Hamiltonian for those fictitious variables, and that wouldn't matter. So you can make this a gauge invariance with respect to that, the Hamiltonian that you use for evolving the fictitious degrees of freedom. Well, with that in hand, that's exactly what we do. And what you see is that when you use that anything there, you will always get the same expectation value, the same ensemble average as you would get as if you didn't have anything there. So that's why the expectation values of all observables are the same regardless of what you have there. So this is our Hamiltonian for that speed boson model coupled to a harmonic bath. And we add that term that corresponds to a harmonic description of the fictitious degrees of freedom for making the calculation easier to implement. But this is what the Bogol-Lyubov transformation is about. You have a set of an creation annihilation operator, and what Bogol-Lyubov realized is that you can write this linear combination of them and generate a new annihilation operator that fulfills the same commutation relation, so long as U and V have their difference of the norm equal to 1. And so that's why, by recognizing that that could be a hyperbolic cosine, this one hyperbolic sine, there's all these various different ways of transforming A into B that will fulfill the same commutation relation. Therefore, there are different ways of representing your Hamiltonian. The particular one that we use in this case is the thermal and Bogol-Lyubov, where we rotate A and A tilde. This A tilde corresponds to the fictitious degrees of freedom according to similar, the same kind of similarity transformation. And therefore, we need to transform our Hamiltonian analogously and the wave function according to the same rotation. With that in hand, then we can obtain that, in fact, the thermal distribution, the initial thermal distribution, is in fact squeezing of the vacuum state. And that's why it's a very good way of preparing the initial condition for the simulations. And as I mentioned before, we add this term with fictitious variables. And once we have this additional term, we have a closed form for the Hamiltonian that is very easy to implement numerically. With that, we have these comparisons where we have the tensor train and thermofield memory kernels used for the propagation of these as elements of the reduced density matrix for various different models where we play with the whole range of parameters that these spin boson model has been analyzed before, and the methodology works very well. And the nice thing is that now it allows us to propagate only a subset. So we can parallelize the calculation, or we can distribute, or we can simplify the computational effort because we have ways of writing generalized quantum master equations for each of them. So this comes very handy at this point, as you will see in a second, for the quantum computing simulation based on these propagators. So what we have is the following. As I mentioned before, the density matrix is vectorized, and the propagator, the superoperator, is matricized. So what we have here is a matrix vector multiplication, but again, it's not unitary. So what we do is we dilate. That means we use an ancilla qubit, so that now the space that represents that initial vector representing the reduced density matrix is twice in size, and but we complete it with zeros. So this would not affect the evolution of the first half as reported after propagation, after applying the propagator into this one, because imagine this is a matrix and the second half of element is zero, so nothing will come into the first half of the output. And this is what the dilation theorem says, is that if you have any contraction, you can write this matrix that would be unitary based on that contraction. So if this matrix is the propagator, I'm applying it to a vector where the second half are equal to zero, then applying this to the first half would be equivalent to the simulation that one wants to perform, which is applying the propagator to this reduced density matrix elements. And with that, we simulated this on the simulators of IBM, and we confirmed that in fact the circuit that is built out of that unitary reproduces very nicely the simulations that we have done with TensorTrain or with the GQME based on memory kernels computed with TensorTrain input functions. But when we went to the actual simulation on the computer, then things didn't go so well. So because, as I mentioned, the circuit depth is beyond the capabilities of existing conventional quantum computers. So at this point, we went to the reduced space, which is where we propagated the dynamics of the diagonal elements only, population only. And in that case, we got much better agreement, simply because the circuit depth is shallower. So that is the, yes. Oh, sorry, who was first?
Sorry. Does this take the propagator as a given from the outside to the algorithm, or?
Yeah, the propagator is built first, and with classically with TensorTrain, and with that you build a circuit. First step. Yes.
So you had this little gadget that you talked about earlier.
Okay.
Slides ago. So never mind.
Yes. This calculations actually I can show you the computer is lemma that looks very much like this. Yeah.
Yeah. So I think it was in the previous slide. This one. Yeah, the gadget. So my question was, why not? Can you use the noise that's already in the computer?
Yes. You can simulate it. Yeah.
Well, no, I mean, so you try to simulate an open process.
Yes,
Computer's got noise.
Sure.
It's got correlated noise. Can you just use that as opposed to trying to run circuits?
Oh, yes.
Killing you?
no, absolutely, yeah. That is an excellent suggestion. That's in fact what we're working on, yes. So I don't know whether everyone followed, but we're trying to simulate dissipative dynamics with a perfect computer. How about using the dissipation of the computer to emulate and to take care of the dissipation part of our dynamics? So yes, so bath engineering for this type of device, in fact, is one of the strengths of the group at Yale, and can be included explicitly. What we don't know is how to define the color of that spectral density well. So only have certain versions of the bath that can be simulated. But that is in fact the way to implement these emulators for the type of dynamics that we are talking about. And that will really bring a lot of efficiency that well beyond what conventional quantum computers can do.
It might also be a good application of crappy quantum computers.
Sure. Sure. No, the physicists are very happy with this stuff.
So what is it that you'll be simulating then? Yeah, you see? No, not over the noise, yeah? Yeah.
Turn on resonators and turn them off.
Say that again?
No, I was just following on Kavan's suggestion that you should use the intrinsic noise of the machine to simulate the dynamics of a noisy system.
Yes.
But my question was, okay, what would you simulate? Because you have no control over the noise of the machine.
Oh no, that's the thing, that it's possible to engineer a specific type of noise with the spectral density, let's say, of the noise of the protein or the noise of the environment associated with whatever liquid is surrounding your. So that's the thing. One could build in noise that is parameterized by your system, and in that case, that would not need to be included explicitly in the simulation. So I think that is yes.
What is the difference between model 1 and model 4?
If I had that memory, no, I have the paper again. Yeah, I don't remember the details of the parameter.
4 looks normal. 1, I can't imagine what can make it look like that.
Yeah, no, but Ethan is very happy with this. So and he has made all the comparisons to QUAPI, so I know they are correct. Don't worry.
This cannot be a two-state system coupled with that.
Okay. So in going in that direction of using the gadget, so the question is now, how do we map the Hamiltonian of the molecular system into a quantum circuit? So how do you program the computer? How do you define the Hamiltonian of the quantum circuit that corresponds to the Hamiltonian of your molecular system? So this is what we've done in this last paper that I mentioned, which is come up with a bosonization method that allows us to write, in fact, any n by n matrix or 2n by 2n matrix in terms of powers, a sum of powers of creation and creation and annihilation operators that could rank from a single cavity to anything that goes all the way to the number of energy levels or dimensions of the Hamiltonian. So in this case, think about second quantization, where you write this operator in terms of A and A dagger associated with J and K. So representing this in second quantization would require 2 cavities or 2 bosonic modes. In this case, we demonstrated that you can do it with a single cavity. And the same thing is for any matrix that is 2n by 2n. Therefore, what we've done is essentially to come up with a way of breaking any Hamiltonian into a set of Hamiltonians that correspond to the modular components associated with that quantum circuit. And what we have applied that approach for is for the FMO model system, where we simulated the population transfer between the chromophores based on this circuit that corresponds to 3 snails coupled to these quartons that induce correspond to the representation of the propagator of this system of chromophores where energy is being transferred. And again, this propagation is based on the dilation theorem and demonstrates that it should be possible to use existing hardware, such as the snails that are coupled with non-linear elements, such as quartons, to represent not only Hamiltonians of molecular systems, but also propagators and dissipators as necessary for the simulation of open quantum systems. So that's in a nutshell what I wanted to tell you, and I'd be glad to entertain questions.
Yes, it's time for more questions.
You mentioned in interesting work. You mentioned in passing that you used the skeleton or cross method for constructing some of the tensor trains.
Yes.
I was wondering what was like exactly the kind of problem formulation when you were using that? Like was it you already had some representation of the full tensor in that case that you were then taking elements from?
Yes.
What was that setting?
Yeah, that's a good question. So as it is known, the tensor train can be built by sequential SVD, but SVD is expensive. In our cases, we always start with a factorizable object, it's a factorizable tensor. Therefore, it can be built directly with Kronecker products. And then that is the object that is used as a reference hit by the propagator that one needs to approximate by this new tensor approximated by the skeleton decomposition. So basically it's comparing to what you obtain with selected elements of the propagated object.
I see. So is it taking advantage of like the idea that you could apply the propagator once at some affordable cost or something?
Exactly. Exactly.
Then recompress.
Yeah, recompress and you adapt the rank. Yeah.
Interesting. Thanks.